illustration of what a geostationary satellite is. So it's a satellite that's at 36,000 kilometers, more or less, above Earth, in an equatorial orbit, circular equatorial orbit, which means that basically it's rotating at the same speed as the speed of the Earth, as the rotation speed. Yes?
So it is orbiting around at the same speed, but is it also rotating on its own, or do you
It's
need
rotating, no, so the satellite remains pointing so that the footprint is always in the same area. The solar panels are rotating so that they stay pointing to the sun. So that they continue to get energy from the sun. So they will stay pointed to the sun, and they'll be rotating like this, while your satellite is always pointing towards the Earth.
And the rotation of the satellite is of natural causes, or is it done by propulsion?
No, so the satellite is natural. It's the panels that have to be guided.
Okay.
Yeah. So this is basically what happens once the satellite has been brought into orbit, put in its position. It looks perfectly well, it doesn't look perfectly geostationary because I'm not sure why the laptop is trembling like that, but once it's there, it's going to stay almost perfectly geostationary. There's small maneuvers that have to be done to maintain it in a box that's defined kind of in a way that you set up a box so that the users on the ground can continuously view the satellite with their 50-centimeter dish. So the box is about 0.1 degrees by side. That's about 150 kilometers. So 150 by 150, and in depth it's about 80 kilometers. In the US, they use boxes about half the size. I think that's purely historical reasons. The regulatory instance gave them smaller boxes. But that's typically the size. We say just if you want to keep it in mind, it's about the box the size of Luxembourg. So your satellite is in a box about the size of Luxembourg moving around. And that's enough mobility so that you have to do maneuvers. So the technology is changing. So the old satellites that had the chemical thrusters, you would maneuver once every week or once every 2 weeks to keep them in this box. So this is what it's like. How did we get there? So the satellite mission is, so you construct your satellite. When it's ready, you're going to bring it to the launch site. There's going to be launch operations that involve fueling the satellite, testing the launcher, testing various functionalities on the satellite. There's some indications here. It can vary a lot. This was one of the SES missions, but they can that can vary. There's a transfer orbit, which is bring the satellite from wherever it was dropped in space from the launcher to where you're going to test your satellite. Then you're going to deploy, because your satellite is basically it's in a box to be put into the launch fairing. You're going to have to deploy the solar panels, the reflectors. So all this is part of the what we call the satellite mission. And then what we call IoT is in-orbit testing. So usually what we do before we bring the satellite to its final orbital position, we're going to put it in an intermediate slot where we start testing everything. So we're going to test the thrusters, test the batteries, test the heaters, test the different channels, test the footprint. And this is typically going to be done before the final handover from the manufacturer. So even if SES is the owner of the satellite before, that's something that's variable. SES can own the satellite sometime between here and halfway here. So depending on the contracts, that varies from time to time. What's going to happen, you have to test all this, and then there's an agreement between SES saying, okay, we looked at the results, we're happy with the satellites, and you get your final payment. Yes?
What is the most ideal situation for SES to own the satellite? Directly at the beginning or only at the ending?
It depends who you ask. The operational teams like to have it earlier because then they have more control of what they can do. In terms of risk, it's easier if it's all the manufacturer, because then they have to handle everything before. But I know the operational teams like to have it earlier because then they have more to say in terms of transfer orbit. And they can decide if they want to speed it up, slow it down, and how they want to monitor things. But with the recent technologies, satellites have become more complex. With cost reductions, you have less people to work because this is all done as a side project again. So it can be more convenient to actually let the manufacturer do this. Operators, there are many operators that are much smaller than SES, and they will usually buy what we call a satellite in orbit. So they'll have a delivery in orbit. And so the manufacturers, they have the manpower and the technology to do this. But yeah, SES likes to follow all of this. I mean, not all manufacturers send someone over to the manufacturing site to follow the construction. Some will just wait for the satellite to be in space. So SES likes to have a view on things, so the operational teams like to have. So it really depends. Yes.
So I think generally, like talking specifically, there should be like 3 different organizations kind of involved in this project which you're showing, because there's a manufacturer who's manufacturing a satellite, then the manufacturer sends it to the launch company.
Exactly, yes.
The launch company is responsible for launching.
Absolutely.
And then it's only
the operator. Yep.
So who handles the transfer of it? Like, is it the launching company?
So the launch operations is going to be the launch company. So that's going to be SpaceX or Ariane handling that. There's going to be supervision by the manufacturer and the satellite owner, but it's going to be handled by the launch company. And the transfer of it, as I said, it depends. I'd say the baseline is the manufacturer. In some cases, it was SES doing the transfer orbit mission, but it's mostly the manufacturer who does it.
And the transfer part is also handled by the manufacturing itself or the launch company? The transfer
No, that's done by the manufacturer. After the last stage has pushed out the satellite, it's in the hands of the manufacturer.
Okay. I'm just trying to understand, because when you try to go for a project, like this is not something that a project with SES would hold. This project is something that a manufacturer should have. Like, it's a project for them. SES is just kind of supervising and has an input to play.
Absolutely. And as I said, there are many operators who are just going to wait for the satellite to be delivered in orbit. They don't want anything to do with this before. SES likes to have the details and to know and to have their say. And typically with the new technologies, so here you have a transfer orbit of 8 days. With the low thrust, we're looking at transfer orbits of 6 months now. If you're doing only electric propulsion, you can have a transfer orbit of 6 months. When we initially bought our first satellite with electric propulsion transfer orbit, basically the manufacturer was suggesting to have thrust continuously with pauses to let the thrusters cool down, but just continuous thrust throughout the orbit. And we had someone do the analysis at SES saying, we're just going to waste too much fuel. If we only thrust during certain parts of the day, we can gain so many months of fuel. Yes?
Yeah, just following up on that, does SES, when you're giving the contract, define the life of the satellite that you want? I mean, when
yes.
So it is defined. So when a manufacturer is telling that this is the orbit that this is the transfer trajectory we are going to take or procedure we are going to take, then won't the manufacturer itself try to guarantee that the 15-year life?
They will guarantee, but if they say we can guarantee 50 years, and SES says yeah, but if you only fire 8 out of the 8 hours out of 24, we're going to have 1 additional month of transfer orbit, but we gain 6 months of lifetime. And again, it's going to be negotiations. It depends on what's in the contract, and these are usually very complex contracts. But it can be debatable, and usually operational teams, and as I say, the good thing when you're talking with engineers is usually they're all curious on both sides, and they're happy to find out stuff. So there may be, constraints that won't allow you to do that, but very often everyone's happy to discuss. And I'm not saying one person's right, one person's wrong, but SES likes to look into the details, understand what's happening, and try to debate it. And they don't always get away with it, but they will say, okay, we think we should do it this way, or at least understand and shadow what's being done.
So, for the launchers, you said that SpaceX and Ariane?
Oh, yeah, there's, I think Soyuz not now part of Ariane. We had many launches with Proton. I'd have to look at all the details, but yeah, those are the major ones. And yeah, I remember being at following a transfer orbit, the transition from the launch operation to transfer orbit. With Proton, it's very easy. Basically, the last stage of the Proton, Proton actually sends out a paper that was, it was like Form 5. It's a typical handover page that they send over, and you get that, and now the satellite's in your hands. And so, I'm not sure how it happens with that, and the handover can be smoother, but sometimes it's very formal. Okay, you get this form, and now you know the orbit, you know where your satellite is, and that's it.
So the geostationary orbit transfer takes much less time, it's 8 days?
Well, it's 8 days if you're using, it can be 8 days if you're using chemical propulsion, if you're using thrust. It varies.
Okay.
But I would say in terms of a week, between 1 and 3 weeks for the classic propulsion systems.
Okay. And so now that with the electric, it's going to take much longer?
It can take much longer. Okay, the deployment, it varies. It varies also as to where you do it. For those long transfer orbits with electric propulsion, you may already be deploying some things earlier. At least part of the solar panels, you're going to have to deploy them to actually get power for your electric propulsion. So this is just a typical standard case. And then the IoT with your in-orbit testing, 3 weeks is a typical value as well. And OSD is on service date. That's when you would start using your spacecraft. But very often this IoT is done at an intermediate orbital position. And you're going to have to relocate your satellite to your final orbital position. And we'll look at that as an example of a project. But before that, just a quick word on the launch operations. So you all know the launch has to be very powerful. The mass of a launcher is about 800 tons. So most of that is just fuel. So a launcher is basically a bunch of fuel tanks, one over the other, that are just, propulsing whatever is in the fairing. The fairing is whatever covers the satellite. So you have 1, 2, or more. Now for the MEO satellites, they're put into blocks of 4, and even then they have a co-passenger. For the GEO satellites, the very heavy ones are launched on their own. Very often you'll have 2 of them. For the LEO satellites, you can have loads of them. I think there was a really nice photo on the internet of the last, what was they called? The white guys who launched 60 satellites, and you can see them all, one behind the other. It was nice. I'll try to find it again. Yes?
Are these rockets only used to launch the satellites in space, or do they also have another use?
Nope, they're just
Launching.
So yeah, as you see, when we call different stages, it's just basically different fuel tanks pushing them a bit further, and every time a tank is empty, it's released. You've probably seen photos of launches. The first stage usually falls back onto Earth and disintegrates. The further stages just remain in space. unfortunately.
More space debris.
And they become space debris. For some rockets that don't launch all the way to, I'll get to in a second.
No, I think usually it's debris for about 6 months, 1 year, but it usually falls back upper stages.
Well, not everything. I mean, if your perigee is low enough, it can fall back. But for things like Proton, who was bringing you very high into space, those never fell back. So depending, if your perigee comes high enough, you're not going to have any drag anymore that's going to enable you to bring back to Earth. And unfortunately, often when you're bringing the perigee up, you're also bringing up the apogee. And if this is going through the geo arc, it's going to continuously come back through the geo arc and be a problem for the geostationary satellites. Yes?
And what's the feel of these launchers?
I'm not sure.
What kind of fuel does they use to for launching it?
I don't know if they're all the same. I'll check that and get back to you. I'll find out.
And for the mission of SpaceX, that the launcher came back to the
Yes.
Earth, and it was the same mission that they were launching satellites and then they came back to the Earth, and is it possible in all of the missions?
No, it has to be specifically designed for that. And it took a long time for them to do it, and it's very impressive what they did. But as it's this one case where it's this stage that's coming back only. It's the first stage that's coming back, but which is already a huge improvement. But yeah, you have to, because you have to have fuel for the return as well. But I think that's one of the projects that Philippe wants you to look into. So it's it'll be interesting. Okay, this is an example of the proton separation. You see how you're going to launch. So you have your first stage, second stage, third stage, and then this is what we call the Breeze M, which is basically a reusable engine that can burn several times. So it's going to stay attached to the satellite and just be like a motor attached to your satellite and just push it several times before it actually launches it. So usually the engines on the launchers just fire and die. Proton had this feature where you had this reusable engine, so you could really target very well whether you wanted to reduce your inclination, increase your apogee, increase your perigee. So we'll have some videos to show you that afterwards. Yeah. This is just a small graphic. So the first separation stage are very close to Earth. So you're launching from a site, and just right after launch, you're sort of letting go of your first stages. You're going to have some ignitions of your first stage, and the Breeze M, you see how they always occur at perigee. First you're increasing your apogee so that you reach geo, and then Proton is launched from a very high inclination site, which is in Kazakhstan. So you have an orbit with a huge inclination, and correcting inclination for a satellite is much more expensive than increasing the size of your orbit. It's about 10 times as expensive in terms of fuel. So reducing your inclination is very important. So we actually use the Breeze M motor to reduce the inclination of the orbit and bring it into an almost equatorial orbit. And see, this is the last burn to bring you to the geostationary transfer orbit. Yes?
Is there any specific spot in the air that would be easier to launch the satellites? For example, near the equator?
Yes, and that's why the French are launching from French Guiana. they're close to the equator, and then you have almost no inclination. That's why sea launch was in the middle of the Pacific, and they were positioned close to the equator as well.
So being near the equator is the best position.
Absolutely, yes. For geostationary launches.
And for each orbit is different.
It can be different, yes. But it's mostly important for whenever you have equatorial launches. But yeah, the main one is geostationary, and then you gain a huge amount by being on the equator. So this is a view from the poles. So if you're looking at the Earth, the breeze M are basically increasing each time you orbit to bring it to a geostationary orbit. So you see, you have these successive burns that are going to bring your orbit to first of all, make it circular, and bring the apogee, the perigee to the geo orbit. So that's a view from the top, and a view from the equator. You see how the inclination is brought down at the same time. And then the one thing I'll bring this back here, then you see the lines here. These are the tracking stations. So I'll show you a short video afterwards, but when you're geostationary, you're staying above the same point on the Earth. So you just need one tracking station to follow your satellite. But when you're in lower orbit, you're orbiting much faster. And you still need to follow your satellite to know where it is. So you're going to need a certain number of tracking stations. So you're going to have to run tracking stations around the Earth and swap over from one to the next to follow your satellite. And you should have, so these are your tracking stations. We had one in Europe, one in South Africa, in the US, and in Australia. And depending on where this is the ground track of your satellite, you're going to be followed by a different Earth station. And just for the fun of it, a little video what it looks like. And you see when the lines are changing, that's when you're swapping our stations. And you'll see, I'm not sure why it's trembling like that. So the burns always occur here and are pushing your satellite. Until you're actually going to reach your geo orbit. So this was a Proton launch for STS-4, so this was a few years back. Ooh.
We have people tracking stations 24/7, I guess.
Yes. Yeah. So this was the mission part. Yes, go ahead.
You made a point that the Soyuz launch, because of the BRIESM stage, it is preferable compared to the Ariane. But then, if Soyuz is launching at such a high inclination, why it is more preferable? Or we use the word, I think, easy.
It's really a negotiation on a case-by-case basis. It's a matter of the price. This was Proton, not Soyuz, but
yeah, okay.
But it's a matter of price. It's a matter of availability. And you know, Ariane is on the equator. They can bring you higher. Proton has the breeze M. Depending on their record, what did they have a launch failure recently? You know, how much people trust. It's really a matter of it's an internal negotiation, and it's also a matter of not always putting your eggs in the same basket. So you're going to have some of your satellites on Ariane, some on Proton. And as you said, sometimes a switchover. If you really have too much delay, switching over from one to it does happen.
So, inclination change is being done with the onboard satellite fuel, satellite thrusters itself?
In this case, it was done with the breeze M, so not with the satellite fuel. With the Ariane doesn't have that feature. So once it drops you in space, it's all done with satellite fuel. So again, that depends on the launcher. It depends. Yeah. And other events that happen are, as we said, the deployments. Then you have the acquisitions for the satellite to do. So you have to, find the sun, find the earth, so that you have your trackers that are pointing in the right direction, and that they can get the satellite to point at the earth. And the orbit testing. All this just to give you some background for the relocation. So that's, you've done all this, you've tested your satellite. Say you've tested your satellite at this position, but you're operating, so this is going to be your longitude. You're going to have to bring your satellite to your final longitude. In this case, at 20 degrees east. Yes. When you're in transfer orbit, you're below the geo arc, so you don't have to worry too much. But once you're in the geo arc, you have other satellites in the way. So you can't just, let your satellite drift through the boxes. So relocating a satellite is an entire project of simply physically moving your satellite, but also avoiding the others, getting the ground station. So here we're moving 4 degrees. You can probably do that with a single ground station, but if it's a longer distance, you may need more than one ground station. So it's all going to be about getting the people, getting the teams to move this satellite and make sure everything is in place. To relocate my satellite we finished testing, we're almost ready, but we still have one last phase to go before we can actually start selling capacity on the satellite. So that's what the relocation is going to be about. So we'll use that as an example to start walking through our project and see exactly what we have to do. I think we have another 15 minutes. Yeah. So, as I said, we're going to have to move the satellite. In this case, we're moving a few degrees. We're going to have our antenna that follows. TT&C is for telecommanding, tracking, and control. So you're going to have a station that's going to follow your satellite. The gateway is the one that's going to be used for the operation. So this one is going to be, it can be the same, but it's probably going to be a different one. It's going to be used for uploading channels and actually using the payload on your satellite. And when you're at your new location, you can actually start using your satellite. In this case, we're going to look at a relocation that's going to be, the last step after the launch phase, and everything that's going to come just before you actually start operating your satellite. But a relocation can happen in many other different contexts. At an end of life, you've finished your service at this position, you've brought in a new satellite, you want to bring your satellite to another location for a different mission. It's used also for what we call bring into use missions. So we sometimes relocate a satellite. It's finished its mission, its commercial mission at the point. It doesn't have enough fuel to be really kept geostationary, so what we'll often do is let it go in inclined orbit, so we just have to control the longitude, but we stop controlling the inclination, which means it's not suitable for all operations. It's suitable for some types of operations, but it can also be used to go to an orbital position and sort of reserve the frequencies, because the frequencies are allocated in a certain way that the International Telecommunications Agency will give you a frequency, but you have to use it within a certain number of years. And if you haven't used it, you're going to lose it, and the next one on the list will get it. So if you know your satellite is going to be launched, but you won't be there in time, you may want to go put a satellite there for a temporary mission, just to book your frequency so that you can still operate your new satellite when it gets there. So this is a luxury of a big operator. Of course, if you have 2 satellites, you can't start playing around with this. But SES now, with more than 50 satellites, has the luxury of doing this, and relocating satellites has become something that happens, I'm not going to say on a regular basis, but we'll have several per year. So it's actually a project, and it's interesting because involves many teams. Even though it looks like a relatively simple aspect, there are lots of people involved. Typically when you're doing a bring into use or have it in the mission, there's lots of regulatory approvals involved. So that's kind of putting the framework. I think we still have time to do, we can just go through the questions. Just is this really a project? I think it's relatively easy answer, right? It's something that's fixed. It's going to have a start and an end. It's not daily operations. It's well defined. You want to move your satellite from here to the very position, and it's not going to be something which is going to have a specific cost because your satellite is there. There will be one aspect of cost here that's not a conventional aspect, is how much fuel you're ready to use to relocate. Because depending on how fast you relocate, you're going to consume more or less fuel. So it's going to have an impact on your satellite lifetime. So the cost will have an impact in some way, but not in the conventional way of how much is it going to cost. Your satellite has been bought, but fuel is going to have a major impact, especially if you launched later than you had to and you want to relocate a bit faster. Are you ready to accept the impact on your satellite lifetime? Those are all questions that you're going to have to ask yourself before you start the project.
And is there any software or something like this to optimize this? For example, to using increasing the fuel and to reaching the long period of lifestyle or
There's not directly software because it's a relatively simple trade-off. You know, if you go, the minimum is 0.5 degrees per day. Yes, was it related?
Afterwards.
Okay, let's just finish it. So the typical is 0.5 degrees per day. That's what was in your budget, and you know that if you go 1 degree per day, it's going to reduce by 2 weeks your lifetime, which may seem ridiculous on a 15-year lifetime. But if you go 2 degrees per day, you're starting to talk months. And in terms of revenue, that may have a significant impact. So there's no real need for software. The equation is relatively simple. It's more the deciding what you're ready to do that's more complicated. So for some satellites that have a design life of 15 years, but an actual lifetime that can be 20-25, you're not going to worry about that. But sometimes you're very close to the design lifetime. Sometimes you arrive in transfer orbit and you're very close to the limit, and then you're going to have to start discussing like, okay, I'd rather have a 1 week delay than having a loss on my lifetime. Yes.
I think
Go ahead.
I assume electric propulsion would not have the issue that it would reduce the lifetime of the satellite, or am I wrong?
No, you still have fuel on with electric propulsion, right? It's not fully batteries. Electric propulsion, you're actually accelerating ions. So you still need to have fuel on board, but the efficiency is such that you worry much less. The concern is different, is that you go a lot slower, or you need much more maneuvers to actually move faster.
But if that area would develop and improve, then it might be a possible solution to really use it without mechanical propulsion.
I don't think they've found anything that allows you to move with no. I don't see how you can move with no fuel at all. Because you still need. I mean, the electric propulsion uses the transfer of momentum, right? If you're not ejecting anything, you're not going to move. So you still need something on board, some fuel on board. There's no wind or there's no air, so there's nothing that can make you push or use the existing air or anything. So you're always going to need some form of fuel. Yes.
This might sound dumb, but Why can't we harness like solar power to charge up the batteries? Or the batteries just are not capable, but like in the future?
We do have solar panels but the batteries are, we do have batteries on board.
Yeah, but harnessing the sun, so to do the electric part, and then you
I
have
was
some
thinking
fuels, so
the
you have a
same.
hybrid system.
But that's what is done, but you still need some fuel on board.
Okay,
You can't do it just with power.
okay, but so they are using.
Because, I mean, when you think of an electric car, it's running the wheels that are pushing on the ground, but there's nothing to push on when you're in space.
I think the general confusion is that when we consider electric propulsion, we compare with electric cars.
Exactly.
But in space, it is always about action reaction. So you have to spit something out.
Exactly.
You're using
It's a
electric
transfer
power to
momentum.
only spit it out.
Okay.
Yep.
Yeah,
That's
I
exactly
was
that.
imagining that you would shoot out electrons, and therefore you could kind of move because even an electron has a mass.
Yeah, but if you're taking the electrons out of something,
Yeah, but you can't
can't-
harness them from the sunlight. No.
not that I'm aware of,
Yeah. Okay.
but
Sunlight gives you only photons, not electrons.
Yeah.
So
Yeah.
there's nothing, yeah, you need some material to push out. So yeah, unfortunately we're still in fuel based. We do use the photons for attitude control at a very minor point. But we do have some solar panels that have like little black flaps to the side that can be used to adjust the attitude. So just the solar pressure. But the solar pressure is not going to be, and the solar pressure you can't control the direction, right? So you can take what you get, but you can't stop it, you can't, it's just there, you live with the solar pressure.
So with these lips, you can kind of sail on sunlight.
Exactly.
Okay.
But it's used just only for attitude, right?
Yeah,
It's,
for
it's
rotation,
not
yeah.
it's not maneuvering you.
And
Yes.
it's not possible to use nuclear power in this case?
The meteor, you would have to catch them or something. I mean,
Because nuclear power is not massive, and it does the same way as the other fuels do.
so in which way would you see using that?
Instead of normal fuel, we cannot use nuclear.
Oh, nuclear.
power.
Sorry, yes. I haven't seen anything with nuclear power on satellites, but
I think the nuclear power will only be a source for your electrical energy. Instead of the sun, you're using nuclear. You still need fuel to
you
put
still
something
need to
up.
push something out at the
You
end.
still need
no?
fuel.
I've read some concepts that follow the problem.
No, it's not about electricity, because nuclear power first produces
A decay, yeah,
explosion and you can use it. But in the electrical power plants, we use firstly the nuclear power generates an
Heat.
explosion,
Yeah.
and then we make it, transfer it into steam. So in the space, I think that we can use this power.
But then, if you're pushing out the whatever decay from your nuclear explosion, you're still pushing out something. You're still getting rid of the material,
Yeah,
and then that's what's going to.
the
generation
the
of
volume of material is lighter and it's less massive.
No, I think as they are, they're already. And the other thing is, I don't think you want to come into the risk of your explosion degenerating on your satellite.
But don't you have nuclear power to send the satellite into orbit or to move it?
To move it, she's
To
talking.
move it.
Just to move it, or either way. I mean, whatever, it doesn't matter.
So the goal would be
On top of that, you don't want such a radiation when you're having electronics up there. You're throwing ions, so it's
Yeah.
going to mess up your electronics. You're going to shield your nuclear generator. I mean, first of all, it doesn't work because, as Professor was saying, you have to push something out. You cannot push.
Exactly, there's no drag,
There's no, yeah. So you need to push something out. You are pushing out the fuel, basically. That is what you're doing. So it doesn't work like in a traditional setup. So we use nuclear power on board in many rovers, but then that is only to generate electricity. That electricity is again used to do something else, to push something out, but then not as a direct power. You cannot use it as a direct power.
Are you talking about nuclear propulsion?
Yeah.
Yeah, NASA and the Air Force have been looking into it for 60 years. There's a lot of problems with it. The fallout is the main concern. Radiation.
But yeah, if you find something with no onboard fuel, I think people will be more than happy, huh? I think we'll leave the next step next time. We'll go through the entire project life cycle for the reorbiting, for the relocation. We'll just, we'll each time do a quick theoretical part, and then we'll actually do the working on the relocation. So you all survived?
Yeah.
Thank you. It was good.
Thank you.
Yes.
You will upload it, the slides in Moodle?
Yeah, I don't have access to the Moodle, but I'll send them to Marielle.
Yeah.
Yeah, I'll send it to the
Thank you.